Hello and welcome to this talk about JAW, which is a framework to study client-side CSRF with hybrid property graphs and declarative traversals. This is the joint work with my advisor Giancarlo and myself Soheil, and we're both from CISPA Center for Information Security from Germany. Let us start by refreshing our knowledge about cross-request forgery, or in short, CSRF. In a CSRF attack, an adversary tricks the victim's browser to send an unintentional forged request to a target website, causing a security-sensitive state change of the server, but without the victim consent or awareness. Now, over the past years, there have been a plethora of defenses proposed to mitigate CSRF attacks, such as refer origin checks, inclusion of hard-to-guess CSRF tokens in the request, or as we've seen more recently, same-site cookies. So having these defenses properly enforced, one may wonder, are we done with CSRF attacks? Are CSRF attacks solved? Well, as it turned out, maybe not entirely, and let me show you an example why. Assume that we have a web application, say bank.com, which has this piece of client-side JavaScript code. The code first reads the URL hash fragment and then, without sanitization, use it as a path of an API endpoint to which an asynchronous request is sent. Note that this request contains a valid anti-forgery token. If you have such vulnerable web application, an attacker can craft a malicious URL and lure the victim into clicking on it. For instance, in this example, the client-side code will send the request to bank.com/API/transfer, resulting in an illicit transfer of funds to the attacker's account. Now, this is an example of what we call client-side CSRF. However, more generally, client-side CSRF vulnerabilities originate when the JavaScript program uses attacker-controllable inputs for the generation of outgoing HTTP requests. So client-side CSRF is very new, with the first instance affecting Facebook in 2018, and our knowledge about this vulnerability is very limited. As such, in this work, our objective is to study this new vulnerability, and specifically, we intend to quantify the prevalence of client-side CSRF in web applications. Also, we are interested to explore the different attacker models and possible types of exploitations. That is, different methods an attacker can control a request, for example, by manipulating the URL, document refer, or web storage, and the prevalence of each method. And finally, we are interested in the degree of attacker control, that is, which fields of a request an attacker can manipulate in real web applications. Now, to achieve our objective, we have to face several challenges that derive from the analysis of JavaScript programs, which is not an easy task. For example, how to create a canonical representation for JavaScript, or how to capture the event-based transfer of control, dynamic web execution environment, or modeling shared third-party library codes. Now, to address these challenges, in this paper, we propose JAW, a scalable hybrid framework for detection and exploratory analysis of client-side CSRF, leveraging property graphs and declarative traversals. At a high level, JAW is comprised of three components: data collection, graph construction, and analysis traversals. At the core of the data collection module is a Chrome-based crawler automated by Selenium that, starting from a single seed URL, crawls the application under test. The crawler is enhanced with a browser extension to collect a set of concrete values observed during the execution of the program, which we call state values. For example, network messages, dynamically fired events, and a snapshot of the global window object, such as window.document or simply the DOM tree. The data collection module will then output the state values and JavaScript code. Then for each web page found, JAW will instantiate a property graph given the code and the state values. To do that, JAW first creates a normalized JavaScript program by concatenating code segments inside script tags and inline scripts, preserving the execution order of the program. Then, using the data collected by the third-party library detector module of the crawler, JAW will symbolically model each library. Given the library symbolic model, normalized JavaScript program, state values, JAW will create a graph called a hybrid property graph, or in short, HPG. Finally, JAW imports the HPG inside the graph database, in particular Neo4j, and then we can declaratively traverse or query this graph using the Cypher query language to explore vulnerable program behaviors, in particular detect and study client-side CSRF. So as you can see, at the core of our framework, JAW is the new notion of hybrid property graph. But what is a hybrid property graph? Basically, if we take three representations of the program, that is abstract syntax tree, control flow graph, and program dependence graph, representing the program's syntax, control flow, and data flow dependencies respectively, and combine these models at the CFG level, we obtain a canonical model called code property graph, initially proposed by Yamaguchi and others for the analysis of C and C++ programs. Later on, Bacchus et al. Added the interprocedural call graph to the canonical representation and used it for vulnerability detection in server-side PHP programs. In this work, we enhanced the canonical representation with additional models. Specifically, in JavaScript, the transfer of control happens not only via function calls, but also via events. For example, when an event is dispatched, one or more registered functions are executed, which can change the state of the program, register new handlers, and fire new events. Therefore, we add the event registration, dispatch, and dependency graph to the canonical representational model to model the event-driven execution paradigm of JavaScript programs. Also, as we will see in the next slide, external libraries constitute over 60% of the total JavaScript lines of code of each web page, and it is essential to model them. For example, the detection of client-side CSRF requires to determine when the program performs an HTTP request by delegating it to library functions. Finally, to address a dynamic web execution environment of client-side JavaScript programs, in addition to the static code representation, we add the dynamically collected state values that are event traces and environment properties. Now, if we combine all these models, we obtain a graph which captures both static and dynamic program behaviors, which we call hybrid property graph, or in short, HPG. For timing constraints in this presentation, I only focus on semantic types and symbolic models. Please refer to our paper for the explanation of the rest of the models. During our evaluation, we observed that external libraries account for over 60% of the total JavaScript lines of code of each web page. This requires existing techniques to reprocess the same code even when visiting a new page of the same web application. As such, we addressed this problem by extracting a symbolic model from each library and used it as a proxy for the analysis of the application code. Let me show you an example. Assume that a web application has a library, a script, say lib.js, which we want to model. First, we construct an HPG for the library, and then we query the graph to identify the nodes that represent native APIs that are known for sending an HTTP request, such as XML HTTP requests, or nodes representing APIs whose value can be under attacker control, for example, window.location.href or simply the URL. And then we assign the type rec and URL to these nodes respectively, which will capture the semantic of these constructs. Then these semantic types are propagated to other nodes following the calculation of the program, that is over PDG, CFG, IPCG, and ERDDG edges, which will allow us to drive the symbolic model for the library by querying the graph for nodes with these semantic types. Similarly, libraries can be part of the data flows of a program, and to reconstruct those data flows, we define semantic types modeling interprocedural input-output dependencies of library functions. For example, we can have the semantic type O_i if the input flows to the output, or O_i if the output is conditionally dependent on the input. Now, these were only a few simple examples of semantic types. For more information, please refer to the paper. Coming to the evaluation, our main questions are the prevalence of client-side CSRF vulnerabilities in web applications, and identifying the degree of attacker control on forgeable requests and types of possible exploitations. As such, we evaluated Java with 106 web applications from the Bitnami catalog, accounting for over 228 million lines of JavaScript code. And we were able to detect 12,701 requests that can be forged by an attacker, affecting 87 web applications. Now, these requests can be forged by manipulating various JavaScript input sources, such as URL or DOM attributes, or document refer, and so on and so forth. Forging each of these input sources require different attacker capabilities. Please refer to the paper for more information regarding the treat model required to forge each input source. Then we systematically look for practical exploitations for 516 forgeable requests. The methodology for the selection of these requests is that we first select all requests across all categories except for DOM attributes or DOM.reads, given the high number of requests of this category. For DOM attributes, we randomly select one request per web application, which results in 516 requests. in total. As a result of our analysis, we created a proof of concept exploits for 203 forgeable requests of 7 web applications, allowing account takeover, deleting user assets, or execution of malicious queries, to name only a few instances. Okay, so we know that there are forgeable requests and they are prevalent, but how bad is the problem? To determine this, we examine the degree of manipulation an attacker can have on the forgeable request, because the exploitation landscape can be influenced by such level of control. Specifically, we characterize HTTP requests via templates, where we encode the type and number of fields that can be manipulated, as well as the type of operation. By examining the randomly chosen 516 requests, we identified 25 distinct templates. Each template reflects the level of attacker's control on the outgoing HTTP request. Let me show you 3 examples of these templates for which we found an exploit. For example, in 185 requests, an attacker can manipulate any part of the domain, path, and query parameter. This means an attacker can forge requests toward other domains too. Then for 20 requests, an attacker can manipulate multiple parts of the request path and body. Finally, for 166 requests, the attacker can only manipulate a single part of the request body, but this level of control could be enough to lead to an exploitation, as suggested by our evaluation. Now, this was only 3 examples of templates. Please refer to the paper for the complete taxonomy of forgeable client-side requests. Summing up, in this paper, we first presented the first systematic study of client-side CSRF vulnerabilities, and to study them, we proposed a hybrid scalable framework that instantiates HPG for each web page starting from a single seed URL, and at the core of JAWS is the new notion of hybrid property graph, a coherent representation for client-side code capturing both static and dynamic program behaviors. And finally, we evaluate JAWS with over 228 million lines of code of 106 popular applications from the Bitnami catalog, and we were able to identify 12,701 forgeable requests affecting 87 web applications. And with this, I would like to conclude my talk. Our code is open source and publicly accessible on GitHub, so I encourage you to have a look and play around with it. Thanks a lot for your attention, and if you have any questions, please don't hesitate to ask.